Welcome everyone. Welcome back to another Ausenco AusIM webinar. For those that haven't been to one of these before, nice to see you. Look, we'll get right into it. I'll only be facilitating today's presentation, and I will. And so most of the speaking will be done by Grant, Steve, and Ben, and I'll help to facilitate questions at the end. So by all means, if you have any questions, feel free to load them into the chat box as we go. Look, the bad news is I've got 3 process engineers with me, and I'm a process engineer as well. So this is a presentation by process engineers, but hopefully it should be broad enough for everybody to enjoy. Look, I've been at Ausenco for about 15 years, and my role is to do with mostly consulting, and I work a lot with Grant, do a fair bit of work on front-end studies, projects, and that sort of thing. Grant is one of the world leaders in comminution, and like I said, we work together quite a lot. Steve Mehring is a tailings dewatering expert who's joined us recently, and he's got extensive industry experience, including running his own consultancy for the best part of the last decade. And Ben Arbudis, I suppose Grant, Steve, and myself are based in Brisbane. Ben is based in Newcastle, down in the Hunter Valley there, and comes with a background of coal processing experience. So today, without too much ado, we'll talk briefly. I'll talk briefly about how technology and value are shaping sustainability. Grant will talk about next generation concentrated designs. Steve is going to talk about developments in tailings and water management. And Ben will talk about some tailings reprocessing strategies that we're seeing in the business. The photo on the right-hand side is a rendered image of a project we did called EcoTails for Goldcorp, and we'll talk a little bit more about that as we go. But that was looking to convert a relatively large lead zinc polymetallic producer into a dry stack tailings plant. So firstly, how technology and value are shaping sustainability. And the photo on the right is a recent photo in the last week. It's our tailings filtration facility at the Las Chispas mine site in Mexico. And I suppose the reason for showing this image is to basically say that a lot of the projects that we're doing at the moment are real and happening. And so today's presentation is a lot about not sort of wishy-washy or far-off things, but real projects that we're actually doing and the industry is adopting, and real approaches to changing materially the sustainability outcomes within studies and projects. So look, I thought I'd start, for those that attended last year's webinar, we had a series and we spoke about the way that we're seeing projects and studies change a little bit, I suppose, and we spoke about studies all the way through to design of projects and operations, and touched on some sort of key themes that we were seeing at the time. And I thought it would be relevant to talk about, well, what has actually happened that we've seen in the business and within the Ausenco business specifically since then. And so up on the screen are just a number of statistics of projects that we've been working on. So the highlights here are that there's a number of coarse particle flotation projects that we're doing at the moment with various technologies. On top of those, there's a whole bunch of other projects that are looking at different, and I've just called them novel recovery methods. So that they might be leaching, or various types of leaching, there might be new types of flotation cells, things like that. I've lumped them in and broadly called them novel recovery methods. Bulk and particle sorting, just in the last 2 years, we've seen quite a few of those. We've done a lot of optimization work, and really anytime you optimize a site, you inadvertently save energy, power, water. So all these improve the tailings characteristics. There's quite a lot you can do just with optimization. A lot of tailings dewatering projects and a number of tailings reprocessing projects, studies, PEAs, all those sorts of things. And so that's how technology is shaping sustainability. And I thought I'll just make one other point before I pass to Grant, and that is how value is shaping sustainability. So it's a good thing, really, that value and ESG outcomes a lot of the time actually do align, despite some of the rhetoric and things that we hear in the media. So that means for a lot of projects, there's opportunities to improve the ESG outcomes and sustainability outcomes by simplifying the design, good design. A lot of it comes down to subtracting rather than adding, simplifying rather than complicating. Relatively basic things, but in basic principles, but the savings in steel and concrete, which have direct correlations to carbon dioxide and other emissions, for example, are real and possible. There's optimizations we can do along the value chain. There was a project we commissioned last year that did a good job of optimizing the interface between a processing plant and a smelter, and really changed challenged the boundaries of what acceptable and what normal contracting offtake agreements would be to give a huge improvement to the overall project. There's all these things I just mentioned around reducing commodities, and ultimately projects still have to manage risks and still continue to manage risks, and a lot of that is around the downside and tailing storage, which you'll hear a fair bit about today. So I'll now pass to, just with that as a bit of context, I'll pass to Grant, who's going to talk about next generation concentrated designs.
Thanks, Matt. That's a really good introduction. I'm really proud of all those projects that have occurred since the last webinar series, and it really shows that these technologies are actually not pie in the sky, but can deliver real value now. So I'm going to talk about a few of those kind of technologies and highlight a few case studies as I go through. So if you can go to the next slide there, please. So when I think of ESG from my perspective as kind of a technical mineral processing engineer, these are the three main areas that I think I'm able to influence directly: water, tailings, and energy. And from personal perspective, when I think of water, I always reflect on whenever I've driven through the Atacama Desert, and that picture on the top right there is actually when I first went to the Atacama Desert. I was driving to a mine in Bolivia, and I was just blown away. You go through deserts in Australia, and there's still little shrubs and plants around and animals. In the Atacama, it's really, they grow rocks there, and that's pretty much it. So water is a real flashpoint, both from an environmental point of view, but also socially. And there's a lot of mines, and we work with a lot of mines that are really unable to access conventional water in those areas, and have to pay a lot of money to desalinate or to pump up seawater from the ocean all the way up the Andes. So that's a real important point there. When I think of tailings, I go back to some of the recent tailings disasters, specifically out of Brazil, the Samarco and particularly the Brumadinho dam failures, image on the left there. And I just reflect on the impact that we can have in communities, and the potential to reduce tailings from a stability point of view and from an environmental point of view, I think is incredibly important, and becoming more and more so. And when I think about energy, I did a lot of work when I was at the University of Queensland on energy, but one of the things that stood out was this image on the bottom right there that you can see of the Sandfire Resources DeGrussa mine, and you can see all of the solar panels that they have installed there, and the code generation of electricity that they've got with solar and diesel. And this is a trend that's pushing in across Australia, at least, and it's going to be something that's more and more important as we progress to reduce our emissions. But we can't just rely on solar panels. I think we need to look at reducing the energy in total. So in terms of the technology that can impact those three areas, I've concentrated on three different technologies here, but there are obviously a lot more. These are just the main ones that I've seen that impact the greatest. So progressive recovery, and I've got a photo there of Ravenswood, and I'll talk to Ravenswood in the coming slides. But progressive recovery is a way of removing waste early on in the value chain before you add water, and therefore you can reduce the water intensity of the final product. Coarse particle flotation, I've got an image on the left there of the installation of a hydrofloat at Cadia that we helped install, and that's been operating for a number of years now, and is really impacting the tailings production. It has the potential to impact the tailings production and also the water consumption by producing a free draining sand, which I'll talk about. And the final one on the bottom right there is really talking about the reduction in comminution energy, and I'll talk to some work that we've done on the vertical roller mill linked with fine particle classification, fine dry classification to produce a finished product. And there's a number of examples of that being promoted at the moment at different sites. So this is just a simplified way of thinking about water usage and tailings production in a conventional processing plant. So the darker blue arrow there shows the ore as it progressively gets processed from blasting, grade control, dig, drive, crush, then milling and separation and tailings down the value chain. And the conventional processing really has a large separation step in the mine, where there's grade control. You draw your polygons in an open pit and dig to those polygons and define what is ore and waste. And in that process, there's a lot of dilution and loss. But then typically all of the ore goes through the rest of the processing circuit, from crushing, milling, through separation, producing a small stream as a product, as either a concentrate or as cathode, and then a large tailings stream that comes out of there. And you can see the light blue at the bottom there is a representation of where the water is used, so added during milling and recycled from the tailings, either in the thickener or in the tailings dam. So I guess in this way, we're really using a lot of energy and water on material that doesn't necessarily add to the final product. A lot of waste goes into this process, and there's large tailings legacies that are left over at the end, and a large amount of water that's locked up in those tailings. If we look at this a bit differently, we can maybe have some technologies that actually produce a waste product along the value chain. So following crushing, some kind of pre-concentration, maybe shovel sorting in the actual mine, bulk ore sorting following the primary crusher, or some natural deportment of value to fines, which I'll talk about in the next slide, that can remove that waste up front. Maybe then as it gets finer, looking at some particle sorting or coarse particle flotation even as we get slightly finer from that. And the whole impact of this is that you can lower your energy and water consumption. There's less tailings per unit product out at the end. So there's less water locked up in those tailings. There's the potential to reduce the capital cost in a greenfields project, or in a brownfields project, you could increase the revenue through the bottleneck, which is normally the milling circuit. So there's a lot of economic impacts of this, positive economic impact, as well as positive ESG outcomes by looking at the processing circuit in this way. So if we move to the next slide, I've just got an example of some pre-concentration work that we've worked on recently at Ravenswood Gold. We're currently constructing their crushing circuit, which has the ability to be able to reject low-grade oversize. They've got a very fortunate ore body where the natural fragmentation of the ore body means that the gold deports preferentially to the fine particles, and the coarse oversize has a very low grade and can be removed as waste. And by doing that, they're actually able to reduce their water and energy intensity by 32%, because they're able to reject 40% of their mass at reasonable recoveries. So this is a great example of where that's possible. There are obviously other technologies that can do this, but it's one of the best ways of reducing your water and tailings intensity. So if we go to the next slide, please. Second technology I really want to focus on is coarse particle flotation. And this is just a graph from a project that we looked at recently, where they were looking at hydrofloat technology, such as what was installed at Cadia that you saw in the earlier slides. And the idea of hydrofloat is that you can actually extend out the coarse particle recovery. So your primary grind, which is on the x-axis of this graph, can be coarsened without a reduction in recovery, and actually a gain in recovery over conventional flotation technologies. So the idea here is that you can, if you've got a brownfield site that is ball mill constrained, you can deconstrain those ball mills by grinding coarser, or if it's SAG mill constrained, pre-crushing prior to it, to be able to produce a coarser product, higher throughput through your plant, and you don't impact recovery. So the value of this is significant, because the capital costs are relatively small in comparison to conventional expansion options. And we're looking at this on a number of different sites. One of these sites at the moment, we're looking at the potential of actually rejecting the hydrofloat tailings, not combining them with the tails as happens at Cadia, but rejecting those tails through a sand plant that can remove the water from the free drain and produce a free draining sand that can then be trucked to a waste dump, or leached potentially, if there is some value there. This is just a schematic of what has been envisaged there, and will hopefully be implementing soon. And through this, you can actually reject 30% of your feed as a free draining sand. You can imagine the impact of that on tailings production and water consumption, just through that simple technology. And the third thing I'm going to touch on is comminution energy efficiency. So this is from some of my work previous at the University of Queensland, where I focused on comminution energy. And really the aim there was to, comminution obviously consumes a lot of the power on a mine. 35% of the power of a mine, it goes to breaking rocks, and that's a huge amount of the global electricity consumption, 2.2%. And if you add into that the embodied energy that of the balls that are consumed in grinding, that adds about an extra 30% to that electrical energy consumption. So it's really worthwhile focusing on the comminution energy. If we go to the next slide, there's some technologies that are available now to be used to reduce that comminution energy. I'm just focusing here on fine crushing and the VRM. Now, obviously, there's also HPGRs that can be used in this to produce this finished product, such as what's being pursued at Iron Bridge, and it's really technology that's well established and used widely in the cement industry. However, applying it to the mineral processing industry has a few challenges. One of which is really, if we're looking at energy efficiency, perspective, the comminution energy, as you can see on the graph on the right-hand side, is almost half of what you would see in an SABC or a SAG milling circuit. However, when you take into account the fan and the heating requirements in the VRM, which is there the classification and ancillary energy, the reduction actually becomes much less, only about 20%. So the challenge really is, how do we reduce classification energy consumption in these technologies while maintaining the comminution energy efficiency? So we want to reduce the lighter blue bars there without increasing the dark blue, which is a real challenge. So if we go to the final slide, there's some takeaway messages. I've just plotted here the tails intensity, the water intensity, and the energy intensity in a per metal product. In this case, I'm referring to copper. And I've just shown the relative potential of each of the technologies that we've looked at: the pre-concentration, the coarse particle flotation, and the vertical roller mill. And you can see in terms of tails intensity, the pre-concentration can reduce your tails by 32%. Coarse particle flotation can reduce those tails by about 21%. And that's a total reduction of over 50% of tailings production, of wet tailings storage that's required. In terms of water, the reductions are similar, over 50% reduction in water intensity by simply the pre-concentration and coarse particle flotation, really. If we can get a dry separation technique that can follow the VRM, then we can reduce that to essentially zero, because the VRM doesn't require water either. But yeah, in terms of energy intensity, and this is, sorry, comminution energy intensity only, not total mine site energy intensity, that can be reduced by over 70% through pre-concentration, coarse particle flotation, and VRM. So these are technologies that are available now, and we've been installing and doing studies on these a lot recently, and I think there's some great potential in bringing these into a lot of different cases. So now I'll hand over to Steve to talk about the advancement in dewatering technology specifically. Yeah, thank you.
Thank you, Grant, and hello everyone. I just thought I'd give you a warning to start, and I'd like to share this picture that I found on a thickener bridge. It says this plant is very sensitive and does not function to specification during visits from VIPs or those who are not personnel of the company. A special circuit in the machine called a critical detector senses visitors and manages emotional state in terms of how desperate he or she is that the plant should operate perfectly. Symptoms may include failure to flocculate, impressive overflow of return water, usually in the form of mud rather than clear water, blockages in the underflow pumps, leakage, etc. These symptoms commonly result in soaked laborers and muddy and panicking managerial staff. So I was basically warned to praise the staff, and if the return water is running at 5,000 ppm or higher, don't worry about it. Do not ask any awkward questions. So that was a sort of a funny that I'd like to share. Today's talk is on technological development, and I want to share with you some of the key technical aspects that we have faced during the last couple of years. And we'll cover basically yield stress, volumes, some costs, and obviously look at some options. And more importantly, I think just recently we've heard that today's the tailings material dictates to us the geotechnical requirements. Previously, we learned that the geotechnical requirements dictated to the process engineer, but we've learned that obviously the material composition is key at the moment. So this slide basically tells us the development of tailings dams. And in the early 1770s, we had direct discharge. That was closely followed by the dams being confined and building walls and basically creating slimes dams or TSFs. Later, the dry stacking progressed, and then in the 1970s, many mines went to mine backfill. And today, obviously, there's been a move to look at maybe reusing, reclaiming, reprocessing old TSFs, and I'll talk about that a little bit later. So Ausenco have assisted customers with different tailings options. We've looked at, in just north of Santiago, we've helped clients with mixing sand and waste rock. The eco tails that Matt was referring to, we've done mixed waste rock and filtered tailings. And at Antamina, we've done a mixture of waste rock, sand, and filtered tailings. So over the years, there's been huge strides made in the method of storage, and as well as things like tailings are progressively getting drier, and they've obviously been driven by the need for water recovery, smaller footprints, and obviously to create less incidents. As Grant had pointed out, there have been a number of tailings incidents. The drive has been to have less seepage, lower closure and reclamation costs, and to give the public a better perception that things are improving. The technologies have resulted in a reduction in the environmental impact. The plant that you see here is one particular option where you could use a hydrocyclone and take the cyclone overflow to a thickener, and the underflow goes to a linear belt filter. This particular plant treats around 8,000 tonne per day of total tailings. The tailings are disposed separately as the thickened fines as a coarse fraction of around 60 to 40% ratio, and the solids content are approximately 60 and 80% by weight, respectively. Next slide. So this is an interesting slide, and I think it's important to understand that we have two scenarios here. We have a mined out pit, and we have the TSF in the background. So due to the geometry of the mined out pit, deposit tailings into the pit generally results in a subaqueous deposition and a significant depth of low density material that will not consolidate, or consolidates very slowly. So thickened tailings prior to deposition basically will reduce the amount of water put into the pit, and with good management will enhance the possibility of maximizing the density of the deposited tailings. The example shown here is an operating mine in an area of great environmental significance. The tailings from the ore recovered from the pit basically was processed and then was stored in the foreground, in the above ground TSF, that's one at the rear. Initially, the tailings were to be permanently stored in the TSF, but a subsequent management decision required that the tailings are ultimately to be reclaimed from the above ground TSF and put back into the mined out pit. Deposit of the tailings back into the pit started in 1995, and the pit, which is 180 meters deep, is now full of reclaimed tailings. So that was a great example of reducing your TSF. This particular slide is basically the ability to pump your tails to voids or mined out voids or pits and perform the thickening duty quite close to the pit to avoid the high cost of pumping thickened yield stress material. So this material is dropped into the pit just to the north of the thickener. And on the right, one can see the options of what can happen. You could consider cyclones ahead of your thickener, and in this particular instance, the cyclone overflow reports to the thickener, and then both the cyclone underflow and thickener underflow then would basically be pumped out as a thicker yield stress material. So over the years, there have been a number of developments in thickeners, in particular larger diameter deep cone thickeners. We're up to around about 45 meters in diameter for paste or deep cone thickeners, and that wasn't possible a number of years ago. There's also been a number of developments in the feed well, basically where we don't have to use as much flocculant, and the settling characterizations have improved somewhat. We've gone to basically larger drive mechanisms, which can accommodate much higher torque. And we've also been able to understand rheology a lot better and move to pumping thick viscous material much further out than previously. So improved flocculant thickness have grown taller as opposed to smaller. So in this example here is a periphery drive of a large thickener, and the drive is actually on the circumference of the thickener, and you could get up to 16 million Newton meter torque on this particular thickener. Next. So the options of tailings has also been basically utilizing your thickener and then pumping this material into a central column discharge. In this particular instance, you can note that the thickened paste is deposited from above and basically falls down and creates a much steeper beach slope. In this case, you're probably looking at 4, 5, even possibly higher degree beach slope. But this is a very effective way of basically pumping your deposit without spending too much on filters. The next option is obviously backfill. We've all heard that you can include pump your material back underground. In this case, you could use a thickener. In one particular application, they use centrifuges and they take out the ultra fines. They add a degree of cement to that paste, and that paste is then either pumped or gravity back into voided underground stopes and pits, and basically backfilled. The other option is obviously dry stacking, and I'd like to thank FL Smith for providing this photograph. And this is the Carrara iron ore dry stack tailings in Western Australia. Ausenco have obviously worked with FL Smith's Rocco and other similar stacking equipment in projects and studies. The unique mobile stacking conveyor solution that has cut water use, costs, and environmental footprint at this iron ore operation. The area has scarce water reserves, so losing so much water to wet tailings would have been costly to both the environment and to the mine. So by doing this, the dry stacking has provided a greater control over the water assets at the site. The other option is obviously to look at dewatering of your tailings using either plate and frames or centrifuges or belt press filters. There's a number of different technologies. This picture here shows the ability to basically treat 100,000 tonne per day of dry flotation tailings. And here we have, can be up to 5 large plate and frame filters. The plate and frame filters are obviously getting bigger from the 2 by 2 meters. They've even gone much larger than that to 2.5. Some are even progressing up to 5 meter plate thickness. So that's really huge. The centrifuge could also be used to dewater, and we've looked at basically solid ball centrifuges with belt versus belt press filters and other options. So in coal, we've helped out a number of clients in disposing of waste, be that dry waste or in co-disposal. We've helped, for example, people with pumping problems and moving both coarse and fines out to the tailings dam. So the other option is obviously you could look at other options of dewatering, dropping this onto a conveyor belt, conveying it out, or putting it in a truck and trucking it out. The important point, though, is that placed tailings will be compact, and therefore will have a lower void ratio and a higher shear strength compared to hydraulic placed tailings. So the high cost of implementing and operating can make a technology appear unfeasible. However, not only economic issues must be considered. Aspects focused on the environmental impact of construction and operation, potential risk to community and environment may make alternate of dry stacking feasible compared to hydraulic pumping to tailings dams. So over the years, we have witnessed a progressive improvement in technologies as we move to dry disposal. This particular pic indicates how we have less water reporting to our dams from the conventional side of 0.4 to 0.6 right down to 0.1. So there's been a good move towards removing the amount of water that has gone out to tailings. And that's about it. And I'd like to now move on to Ben. Thank you, guys.
Thanks, Steve. I'd like to just do a quick recap of the discussion so far. Grant has talked about technologies in the base metal industries that can improve sustainability, specifically by minimising waste streams and in turn reducing power consumption and water usage. Steve then talked about developments in tailings storage and processing, which leads me into the discussion about Ausenco's strategies for tailings reprocessing. I'd like to discuss some opportunities that exist both in the base metal and the coal industries, whereby reprocessing the tailings dam resource leads to great ESG results and is also a financially attractive option. So I'd first like to give some context around why we are considering tailings reprocessing. Tailings reprocessing is not a new discussion. It's been a topic of conversation for a number of years. We now have a greater focus from the market, which is directly driven by investors seeking greener opportunities. And we also have new and novel technologies that enhance the viability of tailings reprocessing. So the market conditions have changed globally. There's more importance on the reduction of waste, elimination of tailings dams, and to be a business with an environmentally conscious focus. The investor sentiment is also changing. So there's greater importance from clients and financiers to have environmentally friendly projects. For instance, there's a group of investors known by the term socially responsible investors, or SRI for short, which, as the name suggests, won't consider investments without first proving they have positive environmental impacts as well as being financially attractive. So people want to be exposed to the mining industry. They just want to do it in a green way. And what better way to do that than to clean up an environmental liability and have a sound investment? Another thing to consider is stakeholder liabilities. Tailings dams create long-term rehabilitation ownership costs for clients through monetary bonds which are held with financial institutions. Now, those bonds will only be released back to the client once they have proven the rehabilitation of the original land. For a typical mine site, this could be a bond being held for a significant number of years and be in the tens of millions of dollars. So these types of large, long-term financial liabilities impede a business's abilities to secure funding for growth projects. By the elimination of tailings dams, you reduce the bonding liabilities for clients and increase the capacity of the business to grow. And perhaps the most important factor to recognise is technology. New technologies and new applications of existing technologies have allowed advances in the minerals processing industries. Typically for coal tailings reprocessing, the limitation is dewatering. So when we look into other industries, it's enabled us to apply novel technologies to dewatering. For example, hyperbaric disc filters and plate and frame filters have enabled more intense dewatering. For resource recovery in the base metal industries, again, we can look into other industries and apply novel technologies to unlock valuable products from a previously wasted stream. For example, the hydrofloat with coarse particle flotation. So these factors outline Ausenco's key strategy, which is to eliminate and rehabilitate tailings dams through their complete evacuation and reprocessing. So we've looked at the big picture context for why we would consider tailings reprocessing. Now we'll look at the reality of the application. And one of the most important factors to remember is that no entire process is 100% efficient at separating the valuable material from the raw ore. This means that there's likely to be valuable material that is going to be misplaced with the rejects. When we look at the minerals industry, we know there's valuable material in the fines tailings. The biggest factor affecting the amount of reserves is the operational history of the mine site. So when you consider the flow sheet, mines typically start up on low capital expenditure, which is aimed to maximise the upfront return on investment for the client. Additional circuits are then added on over time to recover more of the resource. And the period in between is when the valuable material is discarded to the fine tailings, and this can be recovered. For the base metal industries, the head grade can drop off over the life of mine. As technology improves, greater process efficiencies can be achieved. However, the effect of previously high head grades and low process efficiency results in more of the valuable material being sent to the tailings dam compared to the present day. The quality of the ultrafine material in coal tailings dams is important to understand as well, and this is due to the size of the particles. So in general terms, for coal, the finer the particle, the better the quality. And therefore, the product material in a coal tailings dam or a rejects dam could be considered high value. Now, processing consistency is obviously as an important factor as well. And anybody that's spent time in an operational plant will understand that there are periods of poor process consistency. Now, this reduces the overall efficiency of recovery of the resource and can increase the amount of valuable product making its way into the tailings dam. So for the base and precious metal industry, conventional flotation is efficient within the 150 to 30 micron range. The resulting waste streams can have significant value in the coarse, or the 150 micron plus, and the ultrafine, so the minus 30 micron fractions. This is where a technology such as coarse particle flotation can unlock valuable material in the tailings dam within the 300 to 150 micron range. So for the coal industry, there's typically valuable material or low ash product contained within the minus 100 micron fraction. This is important to grasp, that when a plant starts up without flotation and then later on adds in flotation, there's the previously discarded minus 100 micron material can be recovered from the tailings dam. So when we start to build that picture, what's the size of the prize? What are the tailings dam resources out there? So for the coal industry, there are dam resources in excess of 2 million tonnes. In the base metal sector, there are dam resources in excess of 10 million tonnes. We then need to identify the amount of valuable material in the dam resource through test work and engineering. So we've done metallurgical test work for both the coal and base metal industries, and it indicates that the dam resources can achieve yields or recoveries of 50%. We've done additional engineering that confirms that the flotation is suitable and the dewatering is acceptable for a marketable product. Now, it's also critical to understand the dam resource. Tailings dams can have pockets of high concentrations of valuable material where the process had been less efficient, and vice versa when the process was highly efficient. So it pays to spend the time to understand the dam resource completely. So if we look at reprocessing, if we don't reprocess, then the dam rehabilitation must be addressed at mine closure. A tailings dam represents both an environmental and a financial liability. And it's Ausenco's strategy to remediate the environmental liability in a financially viable way. So now we'll take a look at some of the technology improvements that have enabled the unlocking of tailings reprocessing. So Ausenco have been working with clients to bring existing technologies into the minerals processing industries with the HydroFloat and hyperbaric disc filters, to name a few. So when you're bringing in a new technology, you need to do rigorous initial test work. Now that's represented under that past flow diagram there, which required sampling of the resource. Then we do lab test work, followed by a pilot scale design to enable full plant design. Now, during the initial test work, the technologies were proven to be suitable for the application. Additionally, it was also identified that the lab scale test work closely mirrored the pilot scale results, which provided confidence that the lab scale test work could be relied upon for full scale design. We then continued the project to industry funded research. This subsequently was completed to confirm the initial results. Importantly, this then eliminated the need for pilot scale test work. So we also completed, generated spreadsheet calculators, which were created to enable high-level estimation of processing parameters. So, for example, the unit capacity or cake moistures or recoveries. And this was based on readily available resource data inputs. And the future for us is to develop mature process calculations that enable full-scale design directly from resource sampling. So in summary, the key factors that have driven Ausenco's elimination and rehabilitation strategy are the reduction of environmental liability through the complete evacuation of tailings dams, yield and recovery improvements by increasing the total plant product tonnage, maximising the resource by recovering material that would otherwise have been sent to rejects, minimising the cost of rehabilitation by evacuation of the tailings dam and reducing the bonding liabilities, creating reserves by completing core test work across the dam resource and establishing that the indicated resource as a proven reserve in accordance with the JORC code. And finally, it also provides a strong return on investment for investors. So thanks for listening. I'd now like to hand over to Matt Pyle for the Q&A session.
Thanks, Grant. Steve and Ben, that was, yeah, personally found that pretty interesting. Look, we do have a few questions. I'll encourage everyone to enter them into the chat box and they'll get sent through to us, and we will endeavour to get through as many of those as we can in the next roughly 10 minutes. So I suppose the first question, I might start one to you, Grant. You spoke about a number of technologies. What are the barriers to adoption of those new approaches that you're seeing, and how is sustainability assessed and quantified when choosing a flow sheet?
Better unmute myself. Thanks, Matt. No, that's really important. I think some of the barriers to adoption of these technologies is perceived risk, and there can be risk in some of these. For instance, in bulk ore sorting, we currently don't have. We can currently assess the heterogeneity of the deposit or the variability of the grade in the mine, so in situ. But it's very difficult to actually know what grade variability is going to be seen on the belt as it's fed into the plant. So there is a level of risk there, and I think as Ben pointed out, there's the progression, starting off with lab test work, then piloting and removing piloting, just relying on the lab test work, and then in the future, as the technologies are better developed, we can rely just on the calculations. In terms of how sustainability is really measured, I gave some metrics there in terms of water intensity, energy intensity, and tails intensity. I think those are fairly easy to understand, but unfortunately they're not additive. You can't add water intensity to tails intensity and come up with an overall ESG factor. There is some work ongoing in this space. I think there's a few university projects that are looking at this, such as complex ore bodies at the University of Queensland, where they bring together a number of different aspects of this ESG, this complicated landscape, and try and bring that together to something that is easily identifiable and allows you to see where, because there's the potential, sorry, long answer here, there's the potential to reduce the energy but increase the water consumption, or increase the energy and reduce the water consumption. So sometimes these factors are actually competing against each other. So you need to understand holistically, and also that's obviously very site specific. Yeah, thanks.
Thanks, Graham. We've got time for one more. I'm kidding. So I might fire this next one to Steve. Tailings dewatering plants can be very expensive. Steve, can you please share some circuit configurations or ideas to reduce the costs or footprint of the plant?
Yeah, that's a good question. I think the understanding of tailings is the ability to understand what the composition of the tailings basically includes. For example, test work done on a copper tailings indicated that when they had high clays, the thickener, the unit area was required greater area as opposed to easier to process ore. So we have to really understand what the composition is. The other options then would be if this material can be separated, how easily can it be separated? For example, can we use the hydrocyclone ahead of a thickener to reduce that thickener diameter? And then could we segregate the ultrafines from the coarse, and perhaps look at what can be done in that particular instance? So there are various options available. For a great example for a paste thickener in Western Australia, they use both a thickener, a horizontal belt, and a centrifuge. And the centrifuge basically removes a large portion of the ultrafines, which they don't want underground because they tend to be problematic in the settling stakes underground once created a paste. So there are lots of options available, but key to it is understanding what the composition of the tailings and how those tailings are going to basically segregate.
Thanks, Steve. Ben, I've got a question for you here. In addition to reprocessing, the question is, has Ausenco been involved in repurposing of waste, e.g. brick making, agribusiness, in brackets, cropping?
Thanks, Matt.
There's a couple I can add if you...
That's a tough one. To be honest, as Matt's pointed out, I am mostly dealing in the coal industry. I know of a couple of projects that have thought about briquetting tailings before. However, the strategy at the moment is to align ourselves with the investor sentiment, which is to look at ways that we can reduce environmental liabilities. So it's more about what resources out there that we can remediate in a meaningful way that's financially viable. So it doesn't really matter what the process is, as long as we can prove that it remediates the land and is of a financially viable project, then we will consider it.
There's probably a little bit more I can, thanks Ben, a little bit more I can add to that as well. There is the opportunity to make geopolymers out of certain tailings, particularly those that are high in clay. Geopolymers are basically a low carbon concrete substitute, and they've been used, for example, Wagner's have a product called, I think it's called earth-free concrete or something like that. and it's based. They used it to build the Wellcamp Airport out near Toowoomba there. So all the runways and taxi areas, all that sort of stuff is made from that. And there's also, you know, precast concrete substitutes that do that. So and basically that approach is, I think it's a polymerization of the aluminosilicates that are in, or the clays that are in tailings. So there's quite a few people looking at things like that. And I suppose with the right conditions, that will be viable with the right ore bodies and the right, you know, commercial conditions. The sub point there is that there are more and more deposits that are becoming higher and higher clays, simply for the reason that the clays present challenges in processing. So those ore bodies tend to have been left for a little longer. But yeah, it's a good question, that one, and one that a number of people are looking to solve. There's a question here, Grant, back to you. Given the trust deficit that exists between operators and host communities as a result of dam failures, how can resource professionals equip themselves to bridge the gap and raise the trust levels between themselves and communities?
Thanks, Matt. I saw that question came through, and I hope that you weren't going to ask it. It's a really fantastic question, and thanks, Janine Hetzig, for asking it. I think when I talk to my friends about this, I try and discuss it. I have learnt the impact of these dams on communities. So understanding the impact of these dam failures on communities and in different areas, and understanding the historic of that, so that we know that our actions can have a potential detrimental impact, and just talking openly about these kinds of things. I think there's been tendencies in the past to kind of hide these things under a rug, and hope that no one looks there. But I mean, the tailings dam failures fail at 1,000 times the rate of water dam failures. So there is a large risk there in comparison to other dams out there. And I think we need to know that as resource professionals, and we need to be able to discuss that with, I don't know, family and colleagues, friends, and those in our communities, in a real and personal way. That's how I address it. I think there's probably better ways that maybe the AusIMM might be able to address that on a wider scale, and I encourage that to be looked at.
Yeah, there is also training courses and stuff like that AusIMM are offering quite a few of those. So good way to, I guess, get exposed to those elements. Steve, one for you here, and this is I quite like this question. Have developments in thickness been largely incremental, or I guess tailings dewatering, largely incremental changes? Examples: diameter, torque, rheology understanding, or have there been major step changes in the innovations? You're on mute there, Steve.
That's a great question, Matt. And I think maybe we go back in a bit of history and find out what's happened with thickeners. In the early days, we had the smaller diameter thickeners, and they got larger and larger. And I think in the 1970s, they went up to about 130 meters in diameter. Really huge conventional type thickeners with traction peripheral driven drives. And then over the time, we introduced high rate thickeners, and we then found flocculant as being a work of art to help us get the particles to settle inside the feed well. And then slowly we got down from 130, we went down to about 90, 70, and then slowly we introduced high rate thickener, cone thickeners, where we have now the ability to basically control yield stress. But the important thing is the developments of recent is that some recent paste or deep cone thickeners that have been installed in South America have failed. And they have failed recently because of the lack of information understanding the yield stress of this material. So the key driver is not the percent solids in the underflow. I know that is water recovery, but it's understanding that heel stress, the properties that those tailings will basically result in. And we used to design thickeners with 5, 20, 25 K factors. Now, a recent paper presented at the PACE conference suggested we moved to 200, 300, even 400 K factors on the thickener drive. So there's been extensive work being done on trying to understand the rheological properties, because we know we can get up to 60, 65, 70% solids, but it's been the actual properties that have let us down, because once you get to that high percent solids in your underflow, it's the ability then to transport it or move that material to the next area. So yeah, there's been developments across the board, and I think it's been driven more about understanding the rake mechanism and what it will allow.
Yeah, I think it's fair to say there's also been step changes in other dewatering technologies, like solid bowl centrifuges developed specifically for oil sands and now coming into minerals processing and have been introduced into coal for a number of years now on the product side, finding their way into tailings as well. Large scale filters, there's examples of 5 by 5 meter plates being fabricated in filters from Diemi. FLS have a 5 by 3 meter version that they were developing, and for which I showed a photo. There's some information on that publicly available. So there is some of those are step change technologies in terms of the types of material they can treat and their cost.
Yes, and there's key trade-off there as well, Matt. You know, we talk about plate and frame, but we must realize that there's different types of plate and frame. We get the recessed, we get a membrane, we get different types of plate and frame. And so, you know, for example, if you've got a high amount of clays, maybe that is suggesting that we go to a membrane type plate and frame filter press. So those trade-offs have to be considered by looking at the composition of those tails.
Yeah, I realise we are a few minutes over. We might just take 1 or 2 more questions. We've got still a pretty large attendance here, and I apologise in advance. I'm not going to be able to get through all the questions we've got today, but we'll endeavour to get back to all the other questions that we've got. Look, I might finish with one to Grant. Let's see. Are there any other technologies available to look at classification solutions for VRM? What is the issue to do with a lack of alternate technologies, or I suppose what is the challenge to actually reduce energy consumption there?
Yeah, thanks. That's something that we've been looking at very closely. The energy consumption there is really associated with the fan that's required to lift the particles into the air classifier that sits above the VRM table, where the course drops back down. There's very high recirculating loads, so the energy required to lift those particles to the fan is significant. They also need to be really dry to receive a really efficient classification. Now those air classifiers are really efficient, which actually adds to the comminution energy efficiency. So there's this trade-off where you might choose a different classification system that's less efficient, but then that'll reduce your comminution energy efficiency. So we're looking at methods, particularly for the VRM. You can look at overflow methods, so where the material is allowed to flow over the table and then be classified externally. That can reduce your fan energy just by having those classifiers externally and then transported back into the VRM. When you look at the HPGR, which obviously is very similar to the VRM, that's already the system that's in place there. And there's some other technologies that we've been looking at that add a little bit of moisture in that classification, still achieve a very high classification efficiency, but they need to be matched with the VRM or the HPGR that can accept that moisture level without adversely affecting the comminution. So there's a lot going on there, and there's a lot of things that we're looking at in that area, and there's some solutions that we've been developing.
Thanks, Grant. Look, the very last one here, have we looked at any other coarse particle flotation technologies, Bruce Atkinson asks, such as George Novacell? And I suppose the quick answer to that is, yeah, we've been looking at a lot. FLS have some products that are looking quite promising in that space that are adaptations of existing, basically market-ready equipment. Jord has, you know, some quite interesting technologies there that, you know, really have been, I think I first saw some of those presented by Graham Jamieson on Four Corners, you know, in the late 2000s or something, you know. So some of these technologies have been around for a long time. But yeah, there's a number that we're always looking at, and it's a really rapidly developing space. But look, just to wrap up, thanks for everyone's time. Really appreciate all the attendees and all the questions. Feel free to join the next one. There's a save the date there up on the screen for the next Future of Mining Industry and ESG webinar on the 11th of November. And thanks again for joining. I'll pass back to Kelvin from Ausenco. Thank you.